All right, everyone. So welcome to our 590 seminar. Today, Zitao Liao from the Liao group will be sharing about his research with series stack buffers and active power decoupling circuits. Zitao received his bachelor's and master's from the University of Illinois Urbana-Champaign in 2015 and 2017, respectively, and is continuing on to pursue his PhD work in electrical engineering in the Liao group, also focusing on PFC circuits and active power decoupling circuits. So without further ado, here's Zitao.
Hi, everyone. Hi, everyone. So I kind of volunteered this talk because I'm preparing a paper about this, and I think we have enough materials to share some of the exciting results from the kind of reanalyze what the series stack buffer and some optimization results that shows a great reduction in size and improve in power density. So. No, it's not happening. Oh, okay. There we go. So first, I'll just go through like why do we need energy buffer in general in single phase, so DC to AC or single phase AC to DC conversion, and then I'll just talk about like the ideal operation for the series stack buffer, and then just derive the operation constraint, like what are the relationship between all the load level and all the passive components in the buffer. And then since we're now shipping the previous work on the series stack buffer, we're going to do a comparison. And the last part is going to be the optimization of this. How do you, given an operating condition, how do you choose your passive components to be minimized given a certain capacitor type? So and that part is really I have to thank Danny Lohan from the industrial and system engineering, that he helped me a lot by setting the nonlinear programming solver in MATLAB. So let's talk about single phase conversion first. So single phase DC to AC, AC to DC. So on the top there's solar panels where you convert DC to AC. You want to tie to the grid, and so there's EV chargers, data center here, and the power wall also it's kind of bidirectional, where you sell your energy from the solar panel to the grid, and you have the grid charging the battery. It's also in LED industry as well. So there's a fundamental problem in AC to DC conversion, single phase AC to DC conversion or DC to AC. Is basically you have a constant voltage and constant current on the DC side. So your power V times I is going to be constant. And on the AC side, if the power factor is 1, now you will have a sine wave times another sine wave. According to your trig identity, you will have a shifted sign. So if you plot the power, that's going to be the DC power, and this blue curve is going to be your AC power. So you can actually see the average of the AC power is actually the DC power, and all this is position power that if you average that out, the total energy delivered to the load is actually going to be equal to the DC power. So we need to insert a power decoupling device to store. So you store and release the power as we go on with this conversion process from AC to DC or DC to AC. So this is the series stack buffer our group has been working on for like almost 2 years or 3 years. So the operation is really, so now you have, this is your DC source, and this is your DC source current. Now you want this current to be a pure DC current. So and also the voltage on this DC bus to be also a DC. So for constant DC bus, we just modeled the current as a shifted sign current. So there is going to be a DC part, which is IDC, and there is going to be a sinusoidal part, and omega is twice line frequency there because of the twice line frequency energy we just mentioned in previous slides. So we modeled this as the inverter current that goes into the inverter. That's very easy. And then supposedly, if this buffer works perfectly, you should sink all the AC current. So in this branch, it will sink all the AC components here. So the buffer current will just be negative sine omega t. So this two cancels out. And so you can see this is the buffer current. Sorry, this is the inverter current. And this is the buffer current. It adds up to a DC value. So that's how the buffer works. And you just do your voltage and current relationship with the capacitor. You solve for the ripple on C1 with respect to, because this I buff is flowing through the C1. So you just use the I equals C dV/dt, and you solve for the voltage ripple on C1, and there's a buffer converter that generates a complete out of phase AC signal, voltage signal that cancels this waveform. So you got your voltage plot as well. So if this is C1 and this is VAB, so VAB is here and C1 is there, and it also adds up to a DC value. So this node is going to be DC. So this is how it works. It's very easy. It's just some math, sine, cosine that's you can do in high school. So you have this simple math, sine and cosine, because it's a capacitor or inductor. Sorry, capacitor in this case. Now let's just solve for like what is actually on VC2. So now if you look at this two-port, the converter, you can assume a ideal buffer converter. So you say, okay, so the power up here on this port is equal to the power up here on this port. So input output, it's a bidirectional, so it doesn't really matter in this case. So we just say that the converter on both sides is equal. So basically VC2 IC2 equals VAB above. So VC2 IC2 is here. VAB above is on this terminal. And if you look at this, since this is a capacitor, you can kind of say, okay, IC2 equals C dV/dt, and you kind of just have one variable. And notice that this is in the form of a first order differential equation. So if you move the dt to here, and you can solve it, yeah, maybe that's some freshman math, maybe. So you can get the general solution of VC2, and so whenever you solve a differential equation, you will have a constant. Yeah, that's the general solution. And so we'll kind of say, oh, okay, so here, inside the square root, we have a DC term and an AC term. And we define this as the DC energy on C2. So we define C2 has some DC energy on it in the first place. So we rewrite this. You kind of see the format of K is actually energy, right? So 1/2 CV squared. So then we can rewrite this equation, and we find the exact solution for VC2. So that is VC2 DC square. You just replace this guy. So there's not really sure there is some math, but it's not really that hard. And then you kind of since this is a converter, so we wanted to generate the AC waveform here, as we show in the previous slides, ideal operation of the series stop buffer. So it really is, since it's a full bridge, the conversion ratio, this is duty ratio, this is the conversion ratio. So it's really VAB over VC2, which we have solved in previous slides, right? So we don't want this, we don't want the modulation or conversion ratio to be over 1, because this is a full bridge and this technically is a buck. So you don't really have a conversion ratio that can go over 1. So you kind of just derive this equation. You just VAB is solved in slides 3 or 2, and then VC2 is solved in previous slides. So you kind of stare at this equation and say, what is going to be the maximum of this equation? You can take the derivative, but really I just look at it and say, oh, when omega t is 0, this guy is going to be 1, and this guy is also going to be 1. So you have your max out the numerator and your mean at the denominator, and you got the max. So you can kind of rewrite this. So basically, it's the maximum of this duty ratio you can solve in this way. So it's pretty easy, and from the previous step to here, and you just rewrite this more compactly. You will have this design constraint. So this is your magnitude of your how large of a charge swing on C1. That's basically decided by your load and the frequency. In this case, the omega is the twice line frequency. And now you have the DC energy, so the VC2 or DC voltage, and C1 and C2. So this is the relation that this circuit, so C1, C2, and this guy should hold to ensure the normal operation of the series stack buffer. And so once the load is fixed on this side, C1, C2, and VC2 DC are free variables you can choose to optimize for your purpose, right? So sure, and like obviously we have built series stack buffer before, so I'm not gonna go through like in too detail how Shibin derived it. So this paper is a journal paper that's pretty detailed, but I guess I would like introduce the big idea. So like he still uses the current and voltage relationship in the buffer converter. Is kind of the same, where he has this VAB IC2 and IAB IC2, and he introduced this function, this equation that says, oh, I have some initial charge on C2, and I'm gonna, because I'm charging and discharging my C2, I'm gonna have a ripple term, and somehow after all this simplification, he has this quadratic equation to solve the modulation, or I mean the conversion ratio, and you can actually solve it, and here's the equivalent to my constraint. So now we have these two constraints. Like, let's compare, which one is more correct. I don't know. I don't know. So okay, so here, so let's just fix for given load. For given load, let's fix two variables. There are C1, C2, and VC2 DC, and let's just fix two and see like what's the remaining, like what's the requirement for the remaining one. So let's just fix this. IDC equals 2 amps, so like this VC2 max is fixed. And so C1 equals 80 micro, VC2 DC equals 42, because I don't know. You can choose whatever you want. Like you just really just need to verify if they have two different ranges, and if something in between works, then which means the other one will not. It's not like, it's either say conservative or say that if the other, okay, let's just say the results. So so Shibin's constraint gives like C2 has to be greater than 307 micro, and mine is like 68. And you see that it's a huge difference. And if mine works, then it means that Shibin's is too conservative. And if Shibin's work, it means that this might not be a correct constraint, because it just underestimate the constraints. So to verify this, we'll first simulate C2 equals 307 and C2 equals 68 micro. And you can see the waveform here. So here's your VC1, and here's your VABs completely out of phase, and it's producing a DC bus, right? Just like we discussed before. And you can see the ripple using C2. If you have large capacitance, you're gonna have smaller ripple. And this is when the ripple here is gonna be larger because it's smaller capacitance. And you kind of see that. And we'll also verify experimentally with C2 equals 68 micro. And it seems that, with the experimental result, C2 equals 68 micro seems to be working, because it's producing a sine wave that's out of phase with C1. And if we actually plot the the conversion ratio of the full bridge, we can actually see that so when C2 equals 68 microfarad, it's actually very close to 1. where the peak of the conversion ratio when C2 equals to 307 microfarad is only like 0.8. So which means it's kind of say that both constraints are derived based on the condition that the duty ratio cannot be greater than 1. If all the process is consistent, the duration process is consistent, at the limitation, at the boundary condition, the conversion ratio should be 1. But so you like ask this question, I dig a little bit deeper into like why this shows a different result. So you can see here, so this is where the peak duty ratio happens. So I kind of look at these two equations, and you really look at this. So Q2 equals C VC2. So in this case, if you assume a DC part and the AC part, it's not equivalent to this equation. It's not equivalent to my solution because if you see here, inside the square root, sure, there is a DC part and AC part. But the expression is not really, the actual voltage is not really, like outside the square root, it's not really say, oh, I have a DC voltage plus some sinusoidal part. So I think this can be called a first order approximation of Q2. If we look at the power flow in and out of the buffer on two sides, if VC2 has a really, really small ripple, it's almost constant to DC. And so we know that VAB is a sine and IBUF is a cosine, or the other way around. It's going to give you a sine wave. If IC2, if IC2 is also, if VC2 is also a DC value, IC2 is just going to be another sine, and this function will be valid or will be a good approximation. But since we're allowing a large ripple on C2, this approximation in the beginning is already like, assume a small ripple on VC2. So the result might not be, as accurate as the new one. And also, this part is also estimation. The explanation of why this is estimation is a little bit involved, so I'm gonna omit here. But basically, you get the idea that Shibin, just did two estimations and two approximations, and ended up in a more conservative design constraint. So let's just fix one variable now and compare the allowed design space for C1, C2 in this case. So we fix VC2 DC to be 42 volts. And we can kind of plot where the constraints are in this map, in the C1, C2 map, and where the allowed design space. So we plot the old design constraint and the new design constraint. So the orange line, solid line is the new constraint, the old constraint, and the dashed blue line is the new constraint. So, and the design space is any area that's above this curve. So the blue area, which is going to be the new design space, and the strip area is going to be the old design space. And you can see that the old design space is actually within the new design space. And so we can actually also just relate to the previous example where we fixed C1 to be 80 volts. So now we can see the intersect of this line between the two constraints. So this C2 is going to be 68 microfarad, and C2 is going to be, and in this case, it's going to be a 307 microfarad. So another thing I want to point out is that if you look at, if when C2 is increasing, as C2 increases, these two lines actually is approaching. It's approaching. And the reason for that is that, as we mentioned before, the old constraint approximates better as C2 increases or as the ripple on VC2 decreases. So we can also kind of say, so as the C2 goes to infinite, we can kind of solve the limitation on this part and on this part. And it all comes down to this, VC to DC times C1. And this is the asymptote for the C1 value. So if there's no ripple on VC2, then C1's value should be this. And if C2 is much larger than C1, Shubin's constraint will be a good approximation of the series step buffer operation. But at this range, it shows a really huge difference. So this is the buffer that Shubin builds. It's already really high power density, and it's good. It's in terms of design process, in terms of the layout, in terms of the capacitor selection, I think there's already a good amount of effort putting into it. But it seems that by the derivation we just gave, it seems that this can be improved. So the fundamental idea was that can we allow a large ripple on C2 so this guy can be even higher power density? The short answer is yes, but the long answer is that it's not that easy, because as you increase ripple on C2, there's because this is the actual converter. It's not like some MATLAB script. You have to actually consider the components reading and stuff. So let's look at the expression for VC1 and VC2. So for example, you won't have infinite ripple on C1, right? So the C1 ripple has to be smaller than something, than your capacitor ripple reading. Same goes for C2, where there's some ripple, there might be some limit, and most importantly, there will be so the highest voltage seen by the switch is going to be the maximum voltage on C2. So since we already know the expression for VC2, we're now just here's the expression for the peak voltage, and you say it's smaller than your switch reading. And so actually, for example, if you're using a 100-volt switch, you don't want to drive it to 99 volts. You probably just need to drive it to 80 volts. So by switch reading, really, I mean something that's within the tolerance of your switch. So that's by your design choice. And reliability, if you drive too often to the switch reading, then the reliability of the switch might decrease. But that's another analysis we can give. So here are the constraints. Then there's, I guess, plus. So there are 3 component constraints, and there is the operational constraint. And is there a way we can just solve it all at once? Because if you solve it, like before when we were doing a series step buffer design, we solve one constraint and see if it satisfy the rest, and we just go back and forth, and it's a very lengthy process. And if there's a way to just say I'm gonna input all my constraints and it's gonna solve it for me all at once, then that's gonna first of all really standardize the design process of the series step buffer, and it's it also providing a powerful tool that you can incorporate any kind of real component constraints and just simplify the process. So there's a thing called nonlinear programming that Danny Lohan told me. There's an objective function fx, and if there's some constraint, gx, that's your nonlinear equality constraint. So all the inequalities I just mentioned, and then there's hx equality constraints. Maybe you want to use a fixed value of capacitors, you want to fix your C1 to be something, and then you solve the rest. Then you don't really need to have the voltage limitation constraint. Voltage constraint on C1, because you just define what your C1 is. You can use, so you can kind of play around with your component choices and all that stuff. But really, this is a standard way to solve multi-constraint nonlinear problem. So let's first talk about fx. So here we're only trying to minimize the volume of the converter. So we develop and the relation between for a certain type of capacitor, the relation between the volume, the capacitance, and the voltage rating is kind of heavily dependent on, kind of what kind of either being a ceramic capacitor or electrolytic capacitor or film capacitor. So we're really, like in order to compare with the little box design, we limit ourselves to use the same capacitor for C1 and C2 in little box. So, and for ceramics, we need to consider the voltage rating. So we kind of incorporate interpolation, just by using maybe picking 5 points on this line, and we just do an interpolation. If there's any value in between those 5 points, we're just gonna do a linear extrapolation on that. And so the volume function is just gonna be your C1's capacitance divided by, so this guy, so there's the DC voltage bias and the capacitance. So we're just gonna divide it by the capacitance of each capacitor at 400 volts. So since this is on a DC bus, so 400 volts is fixed, and we just times the individual volume of the capacitor. And then for C2, we're gonna do the same thing, but instead of 400 volts, this guy is actually changing with the DC value. So, and do the same thing, you just calculate how many capacitors you need to use and times the volume of each capacitor. And then so this volume C1, volume C2, but really you also need to consider if you increase your voltage, you're gonna have, in order to keep the current ripple the same on the filter inductor, you kind of need to consider the size of the inductor as well. So here it's just like a linear relation between the the inductor and the voltage stress, and it's proposed by Shibing as just a general consideration. When you increase your C2, you're gonna have a larger inductance. Otherwise, you're gonna have like really high voltage, and your filter inductor will be really large, and that kind of if you don't consider this, the real result will be not as, even if you minimize the total volume C1, C2, your total volume is still going to be large because of the inductor. So we need to consider the inductor. But here, I guess a better model can be developed to be more realistic. So we have this volume function, and now let's just say that kind of summarize what we have. So we have design constraints. So first is the buffer operation constraints. I mean, it's kind of small, but you can see this is the operation constraint from the overmodulation condition. And then here's the components constraints. So you have ripple on C1, C2, and your switch voltage stress. So, and the process I'm imagining here is that this constraint is going to give a Liao design space, a 3D design space for C1, C2, and V2 DC. And if you apply the objective function within this 3D space, you're going to have a design choice. So sure, you can, I can like maybe there is a way to, if I work out the math on by myself on paper, maybe it's going to give me some quantitative minimized point, and I can just use that expression. But MATLAB has this really cool function, and that just solve this, it just solves everything by itself. So I don't know how it works. It's kind of magic to me, but maybe Danny knows a little bit like what's going behind the scenes. So the MATLAB nonlinear programming solver is called fmincon. You can import your objective function and all your design constraints all at once, and it's going to give you the best solution. So let's see how that works. Let's say that I have the operation constraint, and I just limit how much ripple I should be on C1. It's going to give me some results. So C1 is going to be kind of, so here's the C1's capacitance, C2's capacitance, and what's the volume on C1, C2. And you kind of see that, if you're using a 100-volt switch, obviously 98 volts is kind of dangerous for you if you have switching spikes and anything that might damage your switch. So in order to compare the results, then we added, say, like, I mean, 90 volts here is still kind of dangerous, but we just want to see like how the multiple constraint imposes on the result. So we just ran the solver again, and we kind of see that it maxes out to 90 volts, and definitely C2 has to increase a little bit. So now this is like everything is automated. Like you don't have to find the expression. Like you don't have to go through multiple loops. Oh, here my switch is maximized. Like the switch voltage reading is kind of high. Then I need to change my C2 and recalculate. Like if you just input all your constraints all at once here, it's gonna give you the solution. So this is really convenient too. I think it's like we should incorporate more design constraints in this case. So everything can be just solved all at once. So here, and so by looking at this results, we kind of see that C2 here is larger and C2 here is smaller. So instead of using a 100-volt switch in little box, maybe we can just use a 150-volt switch. So if we do that, actually, you can see that. So this is the value that's in the little box. So so you can see C2 is actually 430 microfarad, and we can actually reduce it to 80 micro. And since the inductor, actually, another point to make is that the inductor here is actually a little bit oversized. So if you increase the voltage from 81 to 98, the inductor should work. So if that's the case, then we see that why not we replace the 100-volt switch with 150. So the volume C2 can really be reduced by a lot, and the power density really can be improved by 33%. So I think that's a huge improvement considering a technology, any kind of improvements on technology. So I think to follow in that, we definitely need to build. I think we need to build one that can leverage this result. So.
Who are we?
Nathan. So anyway, so here's the results, and we kind of just want to summarize like what's the key point. So the new operation constraint really matches the experimental result simulation more accurately because we didn't really do a small ripple approximation on VC2. And we actually, if you see like the way we solve it, it's really like we consider the power in, power out of the buffer converter, and we just so it's kind of like you solve the energy flow on both sides, and that will give you, instead of solving the charge flow, you solve the energy flow. And the new optimal solution definitely shows great improvements on power density. So some of the future work I really want to expand on this. I mean, the nonlinear programming solver seems to be a really powerful tool to standardize and simplify the design process. So first of all, if we can link to a larger component database, we can just say we can have a more realistic design much faster. Like we don't have to say, oh, is my volume function like realistic, or if I use a different kind of capacitor, how it's gonna change. Maybe one type of capacitor is better than the other, but maybe in terms of efficiency, but maybe one is better than the other in terms of cost or something like that. And so another thing I want to work on is really the loss modeling. So if you remember, there's two boxes of the objective function. One is the volume, and another is the efficiency. So we can, if there's a really accurate model to model, like to reflect the loss in the buffer converter, then we can do a power density vs efficiency trade-off. And then this is the third point is really like the Danny Lohan from the industrial and system engineering he wanted to do. I think it's kind of cool because now if you incorporate the thermal converter dimension constraints, you can really design the whole system all at once. For example, the thermal might be related to your loss, and the converter dimension might narrow down your capacitor choices and your heatsink design. So I think this is a good starting point for future design efforts. And yeah, so I just want to share this early results now. So yeah, that's all my talk. So. Any questions?
So you have this magic nonlinear programmer that gives you an answer. How do you know that it's the optimal?
So one way to think is that, so for example here, if you give this VC2 max to be 90 volts, intuitively, like you should, for the optimal solution, you should have a C2 value that's small so that it drives the ripple to the max you defined. So if this one say, okay, so I'm giving you 90 volts, and if you kind of know that for C2 to be small, like if C2 is at the smallest value, then the C2 max will be this limit you give. So this example here, I'm just adding one constraint, and it shows that it actually limits and it actually solves the best C2 under this new constraint. So I believe this is giving the correct result. So.
Okay.
So you kind of compared your new method to Chabin's old method, your method to Chabin's method, and pointed out that just by dropping down the capacitance, you could kind of validate whether you're there or not. Did you drop it down below 68 microfarads, either in simulation or in hardware?
Yeah, in simulation. In simulation, we did actually. So actually plotted the duty ratio. So this is actually already a little bit over 1. It's 1.00001 in simulation because it's not, so it's in Plex, so it doesn't, and we have a PI loop that's regulating the DC value, so it doesn't really guarantee that it's gonna, and plus like this is actually the minimum is greater or equal to 68 micro. So if we decrease more, it's gonna, like here is really at the limit. If we decrease more, like say even 67, it's gonna, you will see an obvious, I guess like, you will see the conversion ratio is obviously greater than 1 in this case. So.
We can talk about this later, but it'd be interesting to insert a function in Flex instead of the capacitor component.
Yeah.
Because those duty ratios won't be linear like that when you're actually running the nonlinear capacitor.
Yeah, I agree. Yeah. Yeah.
Just a question. You optimize your design for a single operating point, but would it be a trade-off of the robustness of your design? So saying, what happens if your load current increased by 20%?
Yeah. So actually, if you, we actually have a new control method that, so really, if you have a, first of all, you need to design your system to handle the full power, your rated power, right? So from there, from there you can use the design constraints we just talked about. So you can use this to size what's the maximum VC to DC you can have, right? But for each load, actually, if you think about it, this in order for this load to work, in order for the buffer to work at this load, VC to DC can be like any value above VAB, right? But you want it to minimize as much as possible. So this is the lowest point you can get. So in the control, actually vary the VC to DC value according to the load. So the loss will be minimized at like any low point. So we stick. So as you increase the load, then this ripple will be bigger, right? And so this ripple will be bigger, right? So and then you increase VC to DC accordingly. So at all the load, your converter loss is minimized. So because okay, so here if I have say like 30 volt peak on VAB, my VC2 can be like 200 volts. Why not, right? But if that's the case, then you're gonna have a high voltage stress on your inductor and your switch, and your loss will be increased. So you want to minimize VC2 as much as possible at each low point. Yeah. Okay.
I have a question. So I think this optimization method is heavily dependent on the accurate modeling of your system, right?
Yeah.
But we know the real system, they might not be that ideal. So the model might not be 100% accurate throughout all the operational range. So how can you guarantee the sensitivity, relatively controlled?
Yes. Okay. So this is a very good question because if you look back to the derivation of this guy, right? So this is assuming 100% efficiency on the buffer converter. So definitely the converter has losses, and if there is a loss, then so if there's a loss, we have a loss compensation scheme that keeps this C2 constant by introducing a little bit extra ripple on VAB, and which means that, but this is really hard to quantify because you can design your converter to be really optimized, or you can use, like say your switches and inductors might be different. Then it's really hard so that's also one point. If we have a really accurate loss model, then we can incorporate that loss into here and actually solve for the realistic best. But since this is an ideal constraint, you see here, this is the less or equal to. So in your real system, you want to empirically adjust your system to be a little bit above the limitation, because as you said, there is a lot of non-idealities in the real system, right?
Yes. So I was wondering when you show the optimization tool, if you can use a multi-objective. If you can set a multiple objectives in your cost function. Then you will not get a single optimization point.
Yes. So
you get a Pareto from.
Yes.
And you can use your engineering knowledge to select one that is most reasonable.
Yes. Like that's definitely like one of the future work. If you look at here, so like object functions. Now we only have the component volume, and if we have a loss function, then as like you mentioned, there will be a curve. A Pareto from that describes the power density vs efficiency, right? And so based on your choice, you can make your design choices. And actually, to demonstrate how a good design we can operate. So here. This is the experimental results by setting the C2 to 68 microfarad. And you can see here is there's a on top there's a little bit overlap, but actually since the converter loss is relatively small, so we can actually operate at the limit. But I guess as you increase the load, when the loss gets higher, like this limitation, like this VC2 has to set to a little bit higher for the buffer to operate. So.
All right, let's thank our speaker.